No. So it's a pleasure to have Akshay Chaudhari here giving a talk on our weekly seminar. So Akshay is actually an assistant professor of research at Stanford, at the Department of Radiology. And he's been, I think, in California most of his life with a short break in Zurich, I think, with Klaus Pussmann. Yeah. So he did his undergrad in UCSD, then a PhD in Stanford, then a short postdoc at Stanford again, and now he's an assistant professor there. He's actually a very active and establishing researcher, originally in the field in ISMRM community, but I feel like more and more now in machine learning and medical imaging more general. Correct me if I'm wrong, but so it's a pleasure to have Akshay here and looking forward to this talk.
Yeah, thank you so much for the introduction, Ender, and it's a pleasure to be here. Like you mentioned, I had a short stint back, I think almost in 2015, where I spent 3 or 4 months down the street from your lab at ETZ. So some very fond memories of being in Zurich, and it's a pleasure to be back. And for the next 30, 35 minutes or so, I'm excited to talk about some of the latest research from my group, as well as some close collaborators, about trying to use some machine learning based principles to improve MR reconstruction. And really the premise here is MRI is a wonderful modality to give us great diagnostic information. However, one of the biggest challenges that we typically face is MRs, it just takes too long. So it necessarily limits how many patients we can scan. It limits how many new sequences we can add to the patients we're already scanning. So improving the efficiency can hopefully provide better care for patients at a higher value. And I think that's really what drives a lot of the work. And I think it's great to be a part of the ML community, as well as to be a part of the ISMRM community, to really understand what is the clinical significance of some of the tools that we're building out. So excited to chat about that. Please feel free to interrupt at any time if you have questions. I will try to monitor the chat. I have my 3 screens going on here, but the easiest if you just unmute and shout out your question. Happy to have this as interactive as possible. All right, so let's see. Okay, so if we take a very high level 30,000-foot perspective of how the diagnostic radiology process works in general, if we think about a patient coming in for any sort of medical imaging, typically the first step that they undergo is some sort of acquisition of raw data. Let's say if they're getting a CT or a PET scan, then maybe that raw acquisition data could be in the sinogram domain. Maybe if they're getting an MRI scan, perhaps that raw data is in the Fourier domain. But typically, the raw data that we acquire is not actually the image that we have to build. So after any sort of acquisition process, we typically have to learn some sort of forward model, or maybe this forward model is informed by our physics knowledge too, about how to take that raw data and convert that into the image that we care about. And then once we have that image that's built up, the question is, what do we do with it? We can either send it to a radiologist to do their typical interpretation. We can apply our favorite machine learning algorithm, either for detection, segmentation, classification, you choose. So
Akshay, sorry to break you there. I think your microphone is causing a lot of crackling sound.
Oh, okay. Let me,
this is much better.
Jacket, might be my
the jacket, okay. Yeah. Sorry.
Sorry about that. Okay, hopefully this is a little bit better. Okay, perfect. Okay, so this is a high-level overview of how the radiology process really works. And at least here at Stanford, we really try to clump the acquisition and the reconstruction processes into what's known as upstream AI. Everything that comes before the generation of the image, typically your DICOM or your NIFTY file, and then everything after that image has been generated, we roughly term that as downstream AI. Right now, I think these two are separate, but I think going forward, we'll probably be working on some end-to-end algorithms anyway to go from our raw transform domain to the insights that we care about anyway. So if this is a process, I really wanted to focus this talk on this upstream AI part, and specifically for magnetic resonance imaging. And I think the reasons were what I initially mentioned, because we want to make this a high value modality, but fundamentally we're limited by what I like to call this triangle of fate, where we're always trying to choose between 3 sets of parameters. The first one relates to signal to noise ratio of our images. If we scan very quickly, then we'll typically get some pretty poor image quality in terms of SNR. if we spend a little bit longer in acquiring this, maybe we'll be able to improve this, but perhaps this will come at the expense of resolution. And on this right, this image has much higher SNR, but it's just significantly blurred out. But if you want to be able to resolve both signal to noise as well as our resolution, then we'll probably have to give up a little bit on the scan time. So we're always operating within this triangle, and depending on what our clinical indication is and what our clinical use case is, we can pick different points in this three-dimensional ROC curve, essentially. And different institutions will have different practices as to how much SNR is tolerable, how much resolution you actually need. But really, it is hard to escape the trade-offs that we see here. And the reason we really have this trade-off is to understand that better, maybe I'll give you a one-slide description of how MR works. Obviously, there's a lot of simplification in here, but let's say if we wanted to start off with some real image that we want to look at. So this is an axial scan of a knee, and a lot of the images that we'll be seeing in this presentation are from musculoskeletal imaging, mostly in the MRI because that's where most of my background is. I love sports. A lot of my friends are athletes. So I'm really interested in, how do people recover after injuries? How do their joints change over time? So that's kind of my use case that I tend to focus on. So if we want to be able to image this knee, well, the transform domain data that we actually acquire is in the Fourier space. That would typically end up calling K-space. But essentially, that's just a Fourier transform of the image that we're interested in. Once we have this K-space, then we can learn the forward model to go from this transform domain to the image that we care about. And if we simply take the inverse Fourier transform of our fully sampled K-space, then we can generate this very nice looking image. But sampling all this K-space requires time. It is a physical space that we have to traverse. So maybe we can cut corners, literally. Instead of sampling this whole K-space, maybe we can think of different undersampling patterns where we don't have to acquire all these individual points. So we can choose different undersampling trajectories. And with these undersampling trajectories, we have some limited representation of this K-space. But then if we undersample this K-space and simply do our naive forward model to learn the inverse Fourier transform, we'll end up with an image that has aliasing, and there will be very little diagnostic value here. So to be able to generate images that has decent image quality, we really need to be able to smartly sample our K-space if we're thinking about undersampling. And then in addition to this, there's always different trade-offs between our resolution as well as signal to noise ratio. And here's this one graphical description of this. So we implemented actually a new 3D MR sequence that we developed in our lab, tested it out on phantoms, tested it out on healthy subjects, and then deployed it clinically. What we learned during our initial deployment is our sagittal, this is originally a sagittal sequence. Our resolution and SNR in the sagittal plane is very high. Our radiologists love this new fast imaging method. In 5 minutes of scan time, we can scan the whole knee with multiple different contrasts. But as soon as we reformat the sequence into coronal and axial planes, the resolution is a little bit worse. The overall image quality is perhaps adequate, but compared to maybe the sagittal images, maybe you'll appreciate that the coronal and axial reformats have a little bit more blurring. And the reason we actually can't go to higher resolution is because we're fundamentally limited by signal to noise ratio. If the size of our voxel decreases, then our underlying noise statistics remain constant in MRI. So our radiologists would then complain that these images are too noisy. So we're always trying to have our cake and eat it too, but sometimes you really have to give up on one parameter or the other. And to be able to address this initial problem, what we decided to do was turn to our friend computer vision to really see if we can escape that triangle of fate or maybe compromise on some of those parameters. So we tended to use this notion called super resolution, where this has been around in computer vision literature for the last 2 or 3 decades, where the fundamental premise is quite simple. If we have some low resolution representation of an image, can we actually learn those priors and use that information to upsample or convert that image to some high resolution representation? So 2 or 3 years ago, we just wanted to give this a shot to see how well does this work in MRI? Is this even feasible? What sort of assumptions we have to make? So we did a pretty simple study here where we had some low resolution images as an input, and we wanted to be able to convert these to a higher resolution. So we took some high resolution images to start off with. We figured out what the low resolution images would be corresponding to those. We're able to simulate the point spread function. We're actually able to test on the scanner if our simulation platform was actually feasible. And then we essentially trained a pretty simple feed-forward network to learn the transformation between our low res as well as our high res images. And this worked quite well, and perhaps unsurprisingly, based on a lot of the literature that was coming out at the time. And the clinical motivation for this was really, can we enhance diagnostic image quality? So, this is, again, a similar image to what I showed a couple of slides ago. This is a coronal scan of the knee. And over on the left side here, we see this, thin band of tissue. It's called the medial collateral ligament, usually around 1 millimeter or so thick in most healthy subjects. But here, if you want to be able to render any sort of diagnostic verdict, there's just not enough resolution, and there's just not enough image quality to be able to be confident in any of your verdicts. So we actually just use this input image, and we passed it through our super resolution algorithm that we call Deep Resolve, and we're able to see a substantial improvement in image quality. And I will note that these are actually prospectively low resolution scans instead of scans that have simply been simulated. So we deployed this in the clinic. We're able to scan around 50 patients or so with this method. And we saw, pretty decent improvements right off the back. And now if we actually compare this to a ground truth acquisition that took twice as long, we see pretty decent image quality. I wouldn't say that our resolution, our algorithm was as good as the ground truth, but it was significantly better than the input. So we're pretty excited by these initial results. I won't go into the specific results that we found from the study, but we actually had 2 radiologists interpret these input images only. They interpreted the super resolved images as well as the ground truth images. And we saw similar concordance between all 3 of these and the methods that they use for routine day in, day out diagnostic imaging. And we're actually able to compare to arthroscopic findings, which are actually surgical findings. So when the surgeons go in there, so this was exciting. So there are some initial impressions here. So we're actually able to use deep learning, and we're somewhat confident that we could use this to enhance image quality. But then there are also a lot of questions, as one can imagine, that comes up with methods like this. The first one always being the typical super resolution type questions. Well, how are we making sure that we're not hallucinating any features? The high resolution images that we generate, should features actually be there when the algorithm is telling us that those features are there? So that was one fundamental question. And then the second question was, well, we're just treating this as an end-to-end data-driven problem. So it had a fairly moderate data requirement. We trained this on around 120 3D MR sequences, each with 160 slices. So maybe the number of patients isn't terribly high, but this is a very dense, very rich data set that we used. So there's always a need to be able to reduce the data requirements here. And I think this will just be a constant theme in my talk. How can we really do more with less? So the last 2 questions always kept me up at night, I suppose. And I was, even though these methods worked initially, wasn't very happy going forward. So these are the 2 questions we really wanted to investigate. And this is where we've been working for the last couple of years. So maybe very quickly, I'll just pause to see if there's any questions, and I might try to pop up the chat here too, to make sure I can try to monitor that. But any questions for now? Okay, if there's no questions, then I will continue moving along here. So to answer our notion about hallucinating image features and reducing data requirements, how do we actually do this? So I think the simplest answer here is we know things about MR physics. We know how that forward model works. We've been doing MR reconstruction for the last 3 decades. So can we actually inject some of that information into our model in itself too? Can we embed some of these physical principles and help our ML models to be more than just data driven, and by having them satisfy some fundamental constraints. So this approach works significantly better. So say we're starting off with some raw case space in this case. So we have some undersampled case space, kx, ky. And in this example, we also have a temporal dimension, but this can broadly be extrapolated to any high dimensional data set. We can start off with some initial zero field recon, and we get some pretty crummy aliased input images. But instead of simply passing these images into a network for reconstruction, can we come up with useful coil calibration approaches? In this case, we chose E-spared, but really, I think any sort of calibration works pretty well. And it's always better to have some of these calibration maps rather than none. But you can really pick what your favorite is. Nowadays, we just choose between E-spared and JSense. And we feed both of these into a neural network. And what we end up solving for is a simple iterative proximal gradient algorithm, which we've unrolled so that the CNN itself acts as the image regularizer. And we can run this in an iterative manner where there's 2 steps in every iteration at a very high level. The first one is a data consistency constraint. So our neural network, which acts as the regularizer, improves the quality of these undersampled aliased images. But then with those improved images, we want to make sure that we are consistent with the raw case space data that we've acquired already. So if we have some high resolution case space lines that we've acquired, we're just not adding a tiny lesion that shouldn't be there, because everything that our algorithm is learning is subject to this data consistency constraint. So we'll make sure that our data is consistent and then enhance image quality. And that's one iteration. And we can unroll this proximal gradient algorithm over multiple different iterations. And this, in a way, is almost like a recurrent neural network that we're training. You can either update the same weights, or you can have new unique weights across this network and use that to generate our high quality output images. And these remain quite consistent with what you actually started off with. And we've shown some studies, a lot of different groups have shown studies here, that these unrolled methods actually are a little bit more robust. And I think it will help radiologists sleep a little bit better at night too, when we can actually have some of these constraints that we're using to build out these algorithms. And then the additional thing that this buys you is, since we're injecting some sort of domain knowledge into our model, this reduces the data requirements that are needed to actually learn this mapping between our undersample data and coil sensitivity maps, as well as our final image. If you recall some of the super resolution algorithms, they needed like 100+ high resolution data sets. But then here, we only, I forget the exact number for this particular data set, but we're able to train these algorithms with between 5 to 10 subjects where we have fully sampled data. And I think this becomes really important because supervised learning generally works quite well in this case, but it is quite challenging to be able to sample clinical data sets that are fully supervised. So the Fast MRI Challenge, which is a collaboration between NYU and Facebook, I think they've done a wonderful job making that resource available to the community, where we have fully sampled knee MRI data. But from a clinical perspective, that's challenging because typically we accelerate our sequences clinically, maybe 2-fold or 3-fold. So to set up that challenge in the first place, we have to stop that acceleration, and that impacts our clinical service. So it's not seamless. So I think it's really important to think about, can we really go beyond this notion of supervised learning, if at all possible? So this is just the general unrolled model for MR reconstruction that we're learning. And I think it will be the foundation for a lot of the future work that I showed too in the rest of this presentation. And this can broadly be applied to different sorts of data sets. And here, I'll only be showing you a few relevant ones. But with less than 10 subjects, I think this data set was trained with 8 or 9 fully sampled data sets. We were able to undersample by a factor of 8. These are some zero-field images. In the middle, we have some 3D deep learning-based reconstructions. And on the right, we see the reference images. And for me, the deep learning reconstruction and the reference images look pretty identical. And we've shown some of these early results to our radiologists. And some of them actually prefer the deep learning-based precons over the reference, because in some cases, so especially in the back over here, we see some examples of muscle, but our sequence has a little bit low SNR, generally to get this high resolution in the first place. But any sort of DL model that we build out, it's just not capable of fitting to the noise. So it implicitly acts as a denoiser, and we see these noisy images being cleaned up a little bit. So it's just a side win that we're getting for free. But I think it's just very promising that by injecting this domain knowledge into our models, not only are we getting a little bit more guarantees about not hallucinating features that shouldn't be there, but we're fundamentally reducing the data requirements, because MRI, there's so many different MR sequences that one could potentially use. It's really not tractable to have a model trained for each sequence for each anatomy. So I think if we can get past that concern of needing 1,000 fast MRI data set per modality and per anatomy and per contrast, I think that'll generally be beneficial as slowly we transition to thinking about, well, how do we prospectively deploy this into the clinic? So I guess kind of the take-home message here is supervised learning works, and it works quite well. But if we were to take that argument to the extreme, the other question we can ask is, well, instead of having all of our data sets be fully sampled, what if we really have no training data at all? Can we really work in this scenario, and how well could this be applicable? And perhaps this is more of a thought experiment more than anything else, because in the past, even methods that predate deep learning, we've had techniques such as compressed sensing that have worked without the requirements of having fully sampled data. So the reason we started thinking about this was because of this paper that came out, I think in 2018, the Deep Image Prior. I think it's a beautifully elegant paper, and it proposed some really nice theories and observations. And I was really excited to use some of those in the context of medical imaging reconstruction. But generally, this equation, or some variation of this equation, might be familiar to most in the audience. It's just trying to solve some sort of inverse problem right here. And we can pick a sample problem. Let's say we're trying to solve a denoising problem where we have some true image, which is a high signal to noise ratio image X. X naught is some sort of iterative model output that our algorithm is producing. And then X star is just the final image that is produced by this algorithm. And we want to be able to minimize the difference between the true image as well the true highest in our image and our model output. And we do this is an ill-posed problem. So we add some sort of regularization parameter. It doesn't really matter what, but you're adding this term to reduce the search space. So this method is used broadly in signal processing. And if we think about it from an imaging perspective, a very abstract view of the simple equation is when we have this, when we're trying to minimize the difference between our X and X naught term here, what's actually happening is we're searching through all possible images that can be generated. So let's say if we have a 2x2 image, that's 8-bit. So each value can be between 0 and 255. Well, we have the number of possible images that can be generated are 4 to the 256th power. And then what our regularization is doing is actually reducing the search space of those possible images to create something that's actually feasible and to create something that's tractable. So fundamentally here, when we're trying to solve for this algorithm, we're just searching through for the answer in the domain of all possible images. But maybe we shouldn't be trying to do that. Since we know this is an ill-posed problem, can we somehow use any sort of priors, or can we create any priors to reduce that search space and to perhaps replace this regularization term, because it's very tricky to choose what a good regularization is. If our regularization is too strong, our images will just look very smooth, very cartoon-like. And if the regularization term is too high, then our images won't be unaliased, or maybe they'll remain too noisy. So what if we came up with a different model in which we can try to represent these images? So say I have an arbitrary function f, which is parameterized by some parameters theta, and it's initialized by some initial value z. And what we're actually trying to do is, instead of searching for our final image in the space of all possible images, can we search for a final image X star in simply the space of images that can be represented by this function f. And in this case, the function is that the authors use in this paper is a convolutional neural network. They use a simple encoder decoder, and they're able to show that this works quite well without the need for any training data, because this simply takes the place of x naught here, and it reduces the need for regularization. So here's a graphical description of how they showed that this actually is tractable. So on the left here, we have an image of Bill Murray, maybe some Ghostbusters fans in the audience. And what we try to do is we simply fit an encoder decoder to this model. And the goal of this network is to simply recreate the same image as an output. And we'll see that over time, if we're optimizing over this image, our MSE loss goes down pretty smoothly. And at some infinite time step, we essentially end up with zero loss. So our network is fully capable of representing this image. If our network here is if our network here is f, then f can fundamentally create a prior to represent this face of Bill Murray. Next, if our image in question is just the same Bill Murray image with a little bit of noise imposed on top, then we can still see that this algorithm is able to reconstruct this image with pretty high fidelity. There's always some sort of delta between the noisy versus the not noisy image. And I think this goes back to the initial comment that I'd made, is that these neural networks are actually quite, one of the luxuries that we get by training these neural networks for image reconstruction is they can fit to the underlying manifold of the true image signal, but they cannot actually fit to the noise. And because of that, they end up acting as an implicit denoiser. And I think that's why we're seeing this constant gap, because our network is fitting to the background image, but because of the noise, there will always be some sort of MSE residual term. But over time, it can fit for that, even though we never really reach zero MSE loss. So again, this space, this image can still be represented by our function f. So we can search for all possible images, and our network itself is acting as a regularization function. So this was a positive control. And if we simply take all the pixels in this image, permute the combination, so the distribution of pixels stays the same, but there's no clear pattern as we're seeing. Our network here in red is having a really tough time in being able to fit to this and finding a good optimization state. And we can never really reach convergence. And that is nearly identical to if we simply fit noise. If we're fitting this purple curve, our network is just really incapable of learning what sort of family of functions and what sort of weights it should be learning to represent this noise. So maybe I've spent a lot of time on this slide, but I really like this very elegant paper that was put out. And the take-home message is our neural network in itself can act as a regularizer to limit the space of images that we can search through. So we wanted to be able to apply this in the context of MR reconstruction. So the input and output in this case the input essentially would be some noisy images. We start off with some random initialization, and this represents some random init z, and f is just our neural network that we choose. So we're starting off with some random noise, and we want to be able to end up with some sort of fully sampled, nice looking image, but we don't have access to any sort of reference data to train against. So we can't really compute a true MSE loss between our fully sampled image and our undersampled image, because we don't really have access to the fully sampled image data set. But what we tried to do was fit this noise, and instead of choosing the encoder decoder that was initially proposed in the Deep Image Prior paper, there have been improvements that different network architectures act as better priors. So we just used a deep decoder network in this case that simply converts this image z into the image that we care about, because an unaliased high SNR image is fundamentally fittable into the manifold of our neural network in itself. So we don't necessarily need any sort of training data to be able to come up with this image. And if you would have told me this theory, I would have been very skeptical that it works in the first place. But we've been very surprised at how tractable this method actually is. And one of my PhD students, Dave Van Veen, we really wanted to understand, well, sure, it works, but how well does it work? What are some of the failure cases? So we're really interested in analyzing some of this. So here I'm showing you 3 different images. On the left, we have some ground truth images. This is the same image contrast that I showed you on the previous slides, where we had the high resolution in the sagittal plane and slightly lower resolution in the axial planes. So our proposed method in the middle, and this is for 8-fold undersampling of this 3D K-space data. This middle method has been trained without any sort of reference data. And on the right, we have a baseline algorithm, which has been trained in a supervised manner. So our traditional forward model, where we're injecting domain knowledge, where we're using our coil sensitivity maps. And it is pretty hard to see any sort of significant differences between all 3 of these methods. It's hard to claim that the unsupervised method is better than the reference method. But overall, in terms of gross anatomy, in terms of some of these high resolution details, it is very surprising still to me that this method works in the first place. But we're able to show that it can still compete with some of these supervised baselines. And we're able to do some initial calibration studies that we'll be presenting in a couple of weeks at ISMRM. And we showed that this is pretty tractable with 2D fast spin echo scans that have been acquired from the FastMR data set. Excuse me. And we're comparing 2 different metrics here. So we're looking at structural similarity as well as peak signal to noise ratio. And we compare how well does the convolutional decoder algorithm, so the network that I showed you, how well does that work in an unsupervised manner compared to supervised learning? And more or less, we're seeing pretty identical results. Our PSNR might be a little bit higher. I don't necessarily want to claim superiority of our method here, but we're seeing that at least this method can work on par with some of the supervised baselines. And this was also true with our 3D imaging data set using the same method, where we're trying to recreate these images in the KY, KZ space. Those are the 2 dimensions of undersampling. And again, the same conclusions, that our unsupervised convolutional decoder works nearly on par as the supervised algorithm. So maybe I'll take a pause again to see if anyone has any questions about these supervised and unsupervised baselines.
Yeah, actually, I have a question as well.
Yes, yeah.
I mean, it's surprising to me that this happens, given that these networks would see strong aliasing artifacts as structure. So is this with a specific undersampling pattern that you see these?
Yeah, so it really depends on how you're undersampling the K-space, like you mentioned. Instead of having systematic undersampling, so let's say skipping every other line, what we do, at least for our 3D data sets, is we have the luxury of randomly undersampling in our KY and KZ dimension. So because of that, our aliasing artifacts becomes a lot more diffuse. So there's no structured aliasing that we're seeing. And I think that fundamentally helps. So I don't think I have any good images in this presentation to display this. But if we're picking the same acceleration rate, say 4-fold undersampling, with a 2D MR, we cannot undersample in 2 dimensions because that's just not tractable with how MR works. So we're only limited to undersampling in 1 dimension. So that leads to more coherent artifacts. So, and those coherent artifacts do indeed look like structure. So the 4x undersampling for 2D MR doesn't work as well as the 4x undersampling for the 3D MR datasets, but we can really spread the energy of the undersampling that we're seeing. And I think whenever possible, we should create sampling patterns that have a sharp point spread function. So the undersampling aliasing that is generated is diffuse and it's spread across the entire image. That's a really good observation.
My second question would be, when do you decide to stop these algorithms?
Yeah, no, that's a really good question. That was probably the biggest downside of this deep image prior. It really needed early stopping, and the early stopping acted as a regularization function. And honestly, I don't necessarily have a very good answer about what is the best method to do this, because we have no reference to compare against. Some of the newer network architectures that we're seeing, they reduce the need for early stopping and regularization. But what we're seeing right now is even with this convolutional decoder that we're training here, we train this for around like 10,000 updates. And even if we go for 20,000 or 30,000 updates, our image quality still keeps increasing, even though our MSC loss is pretty static. So great observation. If you have an answer, I would love to learn it. But I think maybe what I am pretty bullish about is trying to now create some reference-free image quality metrics to kind of add as an additional prior about when to stop. So if we know about, with these MR scans, one of the benefits that we have is we design these pulse sequences and we implement it in the clinic, so we can tweak them how we want. And for every acquisition, we actually collect some noise statistics only. So if we can somehow use our noise information in a meaningful manner and come up with an SNR map, maybe we can stop when our SNR threshold hits some diagnostically feasible threshold. So I think there's things that can be done. I think mostly that rely on reference-free image quality metrics. But again, very good observation. I don't think I at least have a very clear answer for you today.
Thanks so much.
Hi, Akshay, can I ask one quick question?
Please.
So in this optimization, so maybe I missed something. What is this X0? Is this some kind of a reference image which you have?
It's simply the undersampled case space. So what we keep doing is we keep iteratively moving between the case space, the undersampled case space, and a fully sampled image. So if you kind of imagine our undersampled case space is just a grid of points, what our algorithm really wants to do is fill in those points and to interpolate. So every time our network fills in those points, we can take the inverse Fourier transform and recreate the image. So the network isn't necessarily solving for the image explicitly. It's just solving for a fully sampled case space, and this is where we're enforcing the loss. So we're always trying to stay consistent with the case space that we've acquired.
Okay, yeah, thank you.
Sorry, can I
Any
also
other
ask a question?
Please, yeah.
So you said you have to use these random undersampling masks to be able to not have any structure in the earliest images. Is this still beneficial from the point of view of accelerating the acquisition?
Yes, absolutely. I think it depends on what sort of sequence that we're using. So typically, whenever we're using a 3D sequence, we excite the whole imaging volume, and we read out the 3D Fourier transform. So in that case, we're always fully sampling in our readout dimension, which is kx typically, but we have a potential to undersample in ky and kz. And I think I had an image a few slides ago. Let me see if I can go to that. Here, this one. Sorry, 1 second. Yeah, there we go. So this is kind of what that undersampling grid typically looks like. So the vertical dimension is our ky, so it's how many phase encodes we have. And our horizontal dimension is kz, so how many slices we have. So here in this acquisition, we have 512 phase encode. No, we have, 512 phase encodes and 160 slices that have been acquired. And we have to do this individually. So there's 512 times 160 unique iterations. So we can undersample in the ky and kz space because this is a 3D imaging volume. If we have a 2D sequence, then we can only fundamentally undersample in ky because it doesn't make sense undersampling in kz because you have to traverse that line fully anyway. So there's zero reason why you skip points in kx.
Yes, I understand this. But so did I understand correctly that you, in the phase encode direction, in this case, you have two phase encode directions, you sample 1 point only, or instead of sampling, okay, this is a bit more difficult for me to.
Yeah, so maybe this would help. So we basically have to acquire this 3D data cube of k-space, essentially, and we want to sample that densely. What we're seeing in this particular image, the bottom is kz, the top is ky, and the kx is just going in and out of plane. We always sample that full kx line, and then we undersample in ky and kz.
So in the ky kz plane, we are sampling these points. So essentially, if let's say we have 100 white points here, we require 100 TR That's
Exactly,
the
yeah.
acquisition time.
Exactly. That's just the fundamental of the acquisition itself. The number of TRs that we would need for standard sequences. I mean, things can get complicated with like multiple echo train length sequences. But let's say for simple vanilla gradient echo acquisition, if we have 100 slices and 500 phase encodes, then we'll need 50,000 unique TRs. So if we're undersampling by a factor of 8 in this case, then we're only sampling an eighth of all total TRs that are possible.
Okay, got it. Thanks a lot.
Yeah.
Can I also ask a question, if time permits or otherwise? Maybe
Please,
some other
yeah.
time.
Yeah, I can skip some slides at the end if needed.
Thank you. So another aspect of this is, I guess, the choice of the architecture, because if the architecture is capable enough of representing everything, I guess, then you don't get this denoising property. And I found it also interesting that you used the word coherency, which is more from like the compressed sensing perspective, I guess. But at this point, when you use such a method, you don't actually care about if your artifacts are incoherent because you don't care about sparsity or whatever, going to a sparse domain and so on. So in that regard, maybe these deep image priors are just doing some sort of a spectral filtering, and they tend to filter high frequencies out more than low frequencies, and that's why maybe you see like this improvement and so on. And then maybe also again for 2D sequences, because the artifacts are more in the middle sections of the frequency spectrum, maybe they don't get filtered out as well as in these 3D examples and so on. So the question is like, is there an analysis towards this, like what spectral bands do these deep image priors filter out, and then maybe also create undersampling patterns in accordance with that, or create architectures to increase this effect and so on?
Yeah, that's a very good observation too. And right now, we don't have a good theoretical understanding of what works and why does it work better. We're trying to come up with some, but we've been able to come up with that in some like pretty simple, like 1 or 2 layer networks, but nothing that necessarily represents the true sorts of use cases we're looking at. We have absolutely seen a pretty big dependence on how parameterized your network is. So, like a simple move going from an encoder, decoder to simply a decoder improved the search space and allowed us to have a more compact representation. And maybe going back to your observation about coherence, I think that should still play some sort of role, because I think the aliasing artifacts that we would see when we're undersampling have to relate to, say, what the receptive field is of the algorithm. Let's say if we're simply sampling our k-space and we undersampled every other line, then we know fundamentally that our aliasing will be at field of view divided by 2. So to be able to resolve that undersampling, you would need to have a pretty global receptive field to understand that the aliasing artifact stretches, like half my image away. But now if we're creating incoherent undersampling artifacts, maybe we don't necessarily need that global representation. Maybe we can work a little bit better with their local representations too. So hopefully maybe that can cover the coherence point. And I think you had made one more artifact about just how large these networks can be and how well can they fit to the noise. And that was definitely found with a deep image prior too. If you have a large enough network, you can fit to any signal. Like a fully connected network, for example, is essentially a universal function approximator. So with a deep image prior, we actually saw very big dependence on the size of the architecture versus what sort of performance that we're seeing and its impact on early stopping. There's too many hyperplanes to optimize over. But what we actually saw is when we're using only this like decoder approach, and I'll be pretty honest here, like we tried a few different methods. We're really trying hard to come up with some sort of theoretical basis to justify what works, but I think we're mostly at the empirical hand wavy phase too, if I can be honest. But we've generally seen that we're happier with this convolutional decoder approach because it has a much smaller impact on the size of the network. And it reduces the need for being very good at early stopping. You can be generally good and it still works. So I think there's a lot more work that should be done here to really use this in a tractable manner. And I would love to see a theoretical paper like ICML or something to justify this performance, but we've been struggling with it a little bit. Like everything has been heuristic so far, sadly. All right, so I will keep moving and maybe I'll accelerate slightly. So, okay, so this notion of having only supervised data is great. And this notion of having only unsupervised data also could potentially be useful. But I think neither are really practical scenarios. I don't think we'll deploy algorithms in the clinic with only unsupervised data sets. So I think the more practical scenario is, well, what if I have some fully sampled data that maybe I could get from healthy volunteers? I run it in a research center. And then for all my clinical patients, I only have undersampled data set. So how do we really mix fully sampled and undersampled data is unknown. And I think trying to understand those use case scenarios could be quite useful clinically, because that does simulate what we want to do. And right now, most of these frameworks cannot handle a mix of fully sampled and undersampled data sets. So we turn to some advances in NLP and computer vision, really, to see, can we draw any insights there? And we've been exploring some approaches that use self-training. And maybe very quickly, I'll try to describe what self-training is. So let's say you start off with some fully labeled data sets. Here we're training an ImageNet classifier. This is a bridge, this is a canoe. And we train some basic model, M0. We call this the teacher model with this labeled data set. Then next, we can actually apply this model onto some unlabeled data. And with this unlabeled data, we can create these pseudo labels. And now we can combine our true labels with our pseudo labels and take a larger model and retrain everything together. So there's obviously a lot of label noise, but now our model is maybe larger. Maybe there's a little bit more augmentation, and maybe it's just a little bit more expressive. Then we can just iterate through this process over and over again, where we keep creating new student networks that are learning better and better quality pseudo labels over time. And this method has shown to work really well across a range of ML tasks, especially in vision as well as NLP. So we wanted to see, can we really leverage this for some MR recon work? And I think maybe just two phrases that we should be familiar with here is, a teacher network is a network that creates pseudo labels, and a student network is something that learns, or we train a new model using these pseudo labels that are created. So that's what we tried to do for MR Recon, and this work was driven by one of our PhD students, Belize. So we can create a simple unrolled network that can go from fully undersampled data to fully sampled data sets. And we can learn this transformation because we have the fully sampled data. And this creates a nice positive data pair. And then next, we have some undersampled image only. We don't have the reference for this. So to generate a reference, we can just run inference on this teacher network has been created. And if we run an inference, the image quality won't be great. There'll be some aliasing artifacts because we just learned with a very small domain. But we have these pseudo pairs. Now, once we combine these pseudo pairs with our actual data pairs, we can actually just train a new student network. We can add some consistency regularization. We can add a little bit more. Well, essentially, we're trying to regularize this model a little bit more. But now we're training a new student network with a little bit more true data pairs as well as some pseudo pairs. So this is the general notion of self-training. So we wanted to evaluate this, but then we also wanted to add a little bit of a twist. So now if we have our fully sampled data sets, we can still learn a unrolled fully forward network. And then when we get an unlabeled data set though, instead of using our teacher model, we wanted to use our unsupervised convolutional decoder because our observation was, well, this still works pretty well. So now this data pair that's generated is not from our teacher model, it's from our convolutional decoder or unsupervised model. And then we follow the same procedure and we train a student model for that. And one of the reasons we thought this might work is because the conv decoder might actually be better than most limited data set teacher models, essentially. So with an unrolled teacher with a small data set, we're still seeing these pretty coherent aliasing artifacts, in the femur. But with our unsupervised convolutional decoder image, it's still not beautiful as the ground truth, but it's much better in terms of our unrolled teacher, and it resolves some of those artifacts a little bit better. So perhaps this is a better pseudo label than our typical pseudo label that we'll have with self-training. And that's exactly what we saw here. We ran inference, we tested on 10 or 15 different data sets from fast MRI. This will be presented at ISMRM again, where if we only had one fully sampled data set, this is what our model output would be for a fully supervised baseline. Massive aliasing, not useful at all. If we only use self-training, it's much better than model output, than the supervised output. And I believe here the examples that we're seeing are one fully supervised data set and two unsupervised data sets. So we're still in a very small and very limited data regime. And then when we compare to our convolutional decoder weak labels, we see that that method actually works the best. So I think the goal here really is to explore different ways in which we can combine labeled as well as unlabeled data sets. And I have some results. Maybe I'll kind of skim through them. I think they're just numerical validations, because there's one more set of experiments I want to share briefly. So that was one approach of doing semi-supervised learning with labeled and unlabeled data. But then we tried to come up with another approach that really tries to come up with analogies between compressed sensing, where we're trying to learn denoising as well as reconstruction simultaneously. So can we enforce that in our deep learning model too? And we tried to do that with this model called noise to recon. So let me walk you through this quite quickly. So if we have some fully sampled case space, we can generate an undersampling mask, create an undersampled case space, and try to come up with some sort of model reconstruction that is consistent with our target image. So this is just what our typical supervised baseline is. But then if we only have some new undersampled case space data, how can we still use this in our model? So what we do is we take our undersampled case space and we create additional noise. And then we add that noise to our undersampled case space and have that be passed through a reconstruction network as an inference, which is being performed. So now we have a noisy case space and a not noisy case space. And in reality, we know that the resultant images that we should generate from both of them should be the same. The noise is only in the case space. It does not represent structure. So then between those two variations, we can enforce a consistency loss. So what the network is actually learning in this case is it is learning to denoise our case space, and it is learning to create noise invariant reconstructions. And in this way, we can learn reconstruction, which is through the supervised branch of this network. And we're implicitly learning case space denoising too. And this lets us leverage unlabeled data sets. And what we showed was, I guess this is work driven by two of our PhD students, Arjun and Batu. If we only have, let's say, one supervised volume, where we only have one fully sampled data set, if we only run a supervised recon, we get some structural similarity, some PSNR. Then if we only add noise as an augmentation process, as is done pretty commonly for MR recon, we basically see no benefit. That's the orange bar, and we see that pretty consistently. Actually, in some cases, it actually drops our PSNR. But then if we compare that to this noise to recon approach, where we're still using one labeled data set, but we're using 13 other data sets in an unlabeled manner to learn that denoising, we see consistently higher performance. And maybe these images will do it a little bit more justice. On the left, we have the ground truth. In the second column is some fully supervised scan. The next one is supervised scans with the same noise augmentations, but not in our noise to recon framework. And the rightmost is a noise to recon framework. All the image qualities, I would say, look pretty similar, but our noise to recon network has only been trained with one fully sampled data set versus these other that have been trained with 14 fully sampled data sets. And this is publicly available data from fast MRI. We'll be releasing our code pretty soon after our ISMRM presentation. But again, we thought that this was a pretty interesting way in which we can combine labeled as well as unlabeled data sets. So I had a few more slides, but it's 7 a.m. here, so it must be 4 p.m. there. So I don't know what the time constraints are. I'm happy to talk more, but I want to be cognizant of people's time too. So happy to pause here, take questions. Hopefully there are questions about this semi-supervised approaches. I'm the most excited about those, but yeah, open to questions for now.
Yeah, maybe we can have some questions at this point, and we can go 5 minutes more if that would help. At least for me, it's fine.
Hi, Akshay, for that unsupervised loss, can you go back to that slide?
Yeah.
Yeah, so this undersampled case space, you have both for labeled and unlabeled images, and that you use for this consistency loss.
Correct. Yeah.
Is,
So
is that correct? Yeah.
Yeah, exactly. So essentially, when we're enforcing consistency, we'll have some undersampled case space, and we'll have that same undersampled case space with this additional noise that's being applied to it. And both are.
Yeah, sorry, go ahead. Yeah.
Yeah, and then so we're passing the original undersampled case space through a recon model, and we're also passing the noisy undersampled case space through a recon model, and we're enforcing the consistency on the outputs of both of those. Does that answer your question, perhaps?
No, I meant like this undersampled case space is from the labeled set, right? It's not from some unlabeled image.
It's both, actually. So we can create,
okay.
Yeah, we can create these undersampling masks that we can actually implement on the scanner. We can learn that mask in a fully sampled setting too, and that's where we're simply enforcing the supervised loss. We can have the same undersampling pattern for unlabeled data, or we can have different patterns too. I think generally, as long as we're doing some sort of variable density undersampling, we've seen that our networks are pretty robust to different instantiations of the undersampling mask.
Yeah, thank you.
Yeah. Any more questions?
So is this somehow learning a supervised model, which is also doing some sort of denoising, but the noise is added not in the image space, but in the case space?
Yeah, so the model learning is supervised, but it's supervised in a different manner. It's for the supervised branch of this network, the loss is being enforced between our target fully sampled image and our model reconstruction. So that could be your favorite MSC, MAE, pick your favorite loss. It could be a GAN loss too. And then the other supervised loss is simply between the initial model recon and then the noisy recon, and we can enforce some similar MAE, MSC loss too. So the model training is supervised, but the input to the model is unsupervised because, well, it's semi-supervised because some scans only have this undersampled case space, but the optimization is still creating a loss. We still have to balance, our supervised loss with our consistency loss. So a little bit of a hyperparameter that we can play around with. Does that answer the question?
Yeah, so with that, you hope sort of that your recon model learns how images should look like and so on.
Exactly. The same intuition as compressed sensing, because we want to be able to learn what that general denoising process is. Like if we talk to some of the classical compressed sensing and MR folks, they just say that CS isn't a reconstruction problem, it's simply a denoising problem. So trying to take a little bit of inspiration from that. Okay, perfect. So I'll move ahead. There's maybe 2 slides that I'll go over very briefly. So let's say we've built our favorite model. It doesn't matter, supervised, unsupervised. If we have to deploy it, there's 2 considerations. One is a training and testing distribution shift, and questions about robustness. There was a recent paper in PNAS by some colleagues in Norway that really said that we shouldn't be using deep learning compared to CS Recon. So when I first read that, I wanted to investigate a little bit more. So here's an interesting experiment from the FastMR data set where there's 2 anatomies available in that. We have some brains and some knees. So what we're showing here is what happens when you train only on knees, but then you run inference on brains. We're seeing aliasing patterns still exist, even though our undersampling masks are the same, our color sensitivity masks are the same. So essentially, we're not necessarily learning a forward model to reconstruct images. We're learning a forward model that is conditioned on some underlying anatomy. In this case, everything was conditioned on knee anatomies. And the same thing is obvious in the inverse case, where we train a model for the bottom row on brain MRIs, and then we run inference on knee MRIs. So we tried a couple of different reconstruction approaches, one that used like a simple UNet. We had an unrolled variational network. And both of these learned approaches still have these pretty severe artifacts. But then when we used our unsupervised method, with the benefit of unsupervised method is it's very hard to have biases, inductive biases built into the network that are a function of the data. So it's very hard to be conditioned on a different anatomy if your weights have never seen that previous anatomy. So we generally saw our results here were pretty robust to distribution shifts, because distribution shifts don't really make sense in the context of unsupervised data. So I thought this was quite a promising method to be able to contend with the distribution shifts that we'll eventually see. And then the next experiment that I was pretty excited about too was adding adversarial perturbations. So let me walk you through what this graph really is showing us. So we take our favorite reconstruction method here. This is an L1 minimization, so it's a standard CS, compressed sensing reconstruction. We optimize for perturbations to maximally degrade the PSNR of this image. And we're basically adding different strengths, perturbations of different strengths in the x-axis. And then with the same perturbations, we're running our CS recon, and we're running different reconstruction approaches. So if we optimize for CS adversarial noise, obviously compressed sensing recon is affected the most. The other approaches are affected, but maybe slightly less. If we repeat the same process and perturb our UNet networks, and if we perturb our variational unrolled networks, we see generally consistent behavior with the method that is being perturbed for does the worse over time. And this should be PSNR loss. I apologize. It shouldn't be PSNR. It changes the message pretty drastically. But generally what we're seeing is, with our convolutional decoder approaches, they are robust generally compared to these other methods across these different perturbations that are being applied. And even when we apply a perturbation to the convolutional decoder, we actually, the variational network is affected more by it. So once again, I think instead of thinking that deep learning-based methods are generally non-robust to adversarial perturbations, I think there's a little bit more scope and a little bit more nuance that all methods are actually sensitive to adversarial perturbations, because that is the nature of creating these perturbations. And it should be important to pick the right method to minimize our sensitivity to these perturbations. And hopefully we have some work that's under review in ICML. That's a paper that we shared with the group. Hopefully that can help the community not get scared from using deep learning-based reconstructions, because that was my opinion after the PNS paper came out. A lot of clinicians who are not necessarily used to DL recon and the underlying physics, it's very easy for them to cite that paper and say, hey, deep learning-based recon doesn't work. I don't want it in the clinic. So we really wanted to explain that empirical behavior more. And the point here isn't that deep learning-based networks are not sensitive to perturbations, but the message is all methods are sensitive to perturbations that are optimized to distract them. So the next question is, how do we actually move forward with that? So I thought that was pretty, I was happy to see these results. So maybe as a quick conclusion here, hopefully I've shown you that upstream AI approaches can enhance care, and we can really bake in our physics-based inductive biases into our model to help with model performance, and that some of these new semi-supervised approaches can really help us leverage labeled as well as unlabeled data. So hopefully that opens up a few more doors to building more robust methods. And I'd really like to thank quite a few people who've contributed to the slides, especially the people in bold. All of them are PhD students in EE at Stanford, and they're doing some really incredible work, and a lot of collaborators as well as funding sources. Maybe very quickly, just wanted to make a shout out. We're always looking for postdocs. We actually had a new 10-year funded project, and this is an initiative between 7 different faculty members at Stanford. Fei-Fei Li is working on the computer science side. We have the former chair for bioengineering department, Scott Delp. Gary Gold is the chair for radiology department Ellen Kuhl is the chair for mechanical engineering department. And the goal here, it's really nice to work on a long-term vision, is can we use some medical imaging approaches? Can we use computer vision-based approaches to really model how people move? How do people optimize performance? How can we use those insights using biomechanical modeling with reinforcement learning to learn and optimize for movement, not just to study sick patients, but we're really interested in working with athletes to really optimize performance too, because everything that we've learned about health has been learned by studying sick people. So can we have a different insight where we really study Olympians, where we study pro-level athletes? So I'm super excited about this. Also super excited about any other project that I mentioned here. So always happy for you to contact me, always happy to brainstorm and chat. So thank you again for having me. Apologies for running a little bit over time, but the discussion has been great and this has been super fun for me.
Thank you so much, Akshay. Thank you very much. This was a fantastic talk, and I think it hit a lot of common interests, and I'm sure we will talk quite a bit about this talk afterwards in our meetings.
Well, hopefully good, but feel free to send criticisms too. I think there's a lot of work to be done. I think I've only showed like some results that work well, but it's like it has been pointed out previously, I think it'll be better to have some more theoretical rooting for a lot of this. So always excited to chat more. If anyone's interested, we can definitely try to figure out ways in which we can work together and answer some useful questions.
So with that, I'm sure there are questions. I have to leave for a meeting with some physicists who talk about stuff I have zero understanding of. So yeah. Thank you very much again.
No worries. I'm happy to stick around if any of the students have any questions over the next 5-10 minutes or so.
Thank you.
Bye, Ender. Enjoy the day. Are there any questions I can try to answer here?
Hi.
Sorry.
All right, you can go first.
Okay, so I guess thank you for a good talk. So I had a question about robustness, and have you looked at robustness over different understand patterns, kind of? So what happens if you train on radial understand patterns and then test on other Cartesian, for example?
That's a good question. We haven't investigated that a little bit more. And one of the initial reasons that wasn't a very, on our list of looking at different distribution shifts, that distribution shifts can come across in many dimensions. We have these anatomical distributions, we have network-based distributions, and then we can have sampling-based distributions too. But one of the reasons we didn't consider too many sampling trajectory-based distribution shifts is because we can always control for that. We design the MR sequences, and it matters less, even if you're on a Philips MR scanner, a Siemens MR scanner, or a GE MR scanner, 2D fast spin echo will more or less be undersampled in the same manner. The only question will be, is it uniform or random undersampling? If we go to 3D MRI, there has been a lot of work about trying to find what is the optimal sampling trajectory. Can we use reinforcement learning? Can we learn that in a data-driven manner? But I always find that the answer from all those papers is always the same. It's some sort of variable density undersampling pattern. The only question is, how much to undersample, less how to actually spatially undersample. So I think it would be interesting, but given kind of like the clinical scope that we had, we chose, at least for now, not to look into it. So I don't necessarily know what the results would be from a robustness perspective. From a general perspective, based on what's worked for us, generally variable density undersampling works a little bit better. And if you've trained with enough undersampling masks, most of your models are pretty robust to even new mass distributions that we haven't seen during training time. But that's empirical.
I see. Thanks.
Yeah.
Hi, can you hear me?
Yes.
So actually I have two questions. So the first one is like, what's the barrier like between the super resolution of natural images, so like photos or something, and between medical images? Because like I'm doing a semester project on super resolution on natural images, And I was wondering, like, if you so you want to add small details to the an MRI image, and the one thing that we need to make sure that these those small structures has an anatomy meanings, like it have kind of a medical sense. So how can you make sure that it have the medical sense? It's not just like adding some random structures on the image. So like, I think for natural images, we just need to make sure the image looks good. But for medical image, I think the image has to have some kind of meaningful medical meanings.
Yeah, and I mean, that's where a lot of these data consistency approaches really come in. We're not hallucinating new features because we're always being consistent with the undersampled data sets that we've acquired. So as long as we're always enforcing for that consistency between our improved image and our actual undersampled data, we can ensure that there is no new artifact which is being created. And I think lastly, we have to validate this clinically. I can build best looking images. I can be super happy with it, but I'm not the radiologist. I don't look at these day in, day out. So I think that really should be used to close the loop. I described in some of the super resolution work where we deployed that clinically. We looked in like 50 patients that were consecutive at our Stanford hospital. And we had 2 different radiologists read the super resolved images and they read the normal images. And they didn't find too much of a difference. But visually looking, if you're looking for differences, they do show up. So using some of these data consistency constraints is probably key. But you can still use the insights because now you know how to train a good forward model in terms of a good image-to-image network. So we can just use that as an update block in our unrolled network anyway. So I think the super resolution part is just a small part of our deep learning-based MRI reconstruction model.
Okay, I see. Thank you. The next question is, I'm just curious if it's possible to like interpolate the Fourier space, so the K space, like we only sample all the so like the central part which contains like not the details but like the main structure of the image, but we interpolate the Fourier in the Fourier space.
Yeah, so that's performed pretty commonly on scanners too, Fourier interpolation. Usually people use that. So let's say if you're acquiring an image that's 128 by 128, and that's densely sampled, the output image that you see from that will actually be 256 by 256 in the DICOM dimension, because people simply just pad the edges with zeros to increase the dimensionality, but you're not really adding more detail. And people have tried interpolation approaches, but it's very hard to interpolate in K-space. And that's why approaches like parallel imaging have come up, because that uses your knowledge of your coil sensitivity patterns to constrain the possible interpolation kernels that you can learn. But that is just the foundation of things like GRAPPA and SMASH-based methods. We're interpolating smartly using some data-driven kernels, essentially. So the intuition is absolutely correct, but I think simply interpolating will probably not work because we're not leveraging information about the coil sensitivity patterns, which can really reduce the scope of how ill-posed the problem is.
Okay, thank you.
Can I ask another question if you have to?
Please.
So my question is regarding the evaluation of these things. So when we evaluate reconstruction results, we usually look at some healthy images because they are more abundantly available at the end of the day. And we usually look at PSNR or RMSE or whatever. Mm-hmm. And if you even have images, unhealthy images with MS lesions make up, I don't know, maybe less than 1% of the image. So their effect on RMSE and so on is really low. And at the end of the day, we design these things to scan non-healthy people to see those lesions and so on. So there is somehow a gap between how we evaluate these algorithms and how we want to use them, actually. And I wanted to hear your opinion because you're also closer to the radiology and so on, like in a technical lab. So.
Yeah, so I mean, I think the easiest approach is to be able to train on a diverse data set. Obviously tricky because, there's not that many that are available. The fast MRI data set is nice because it's all clinical cohorts. We're actually planning on releasing our 3D QDES data set. So those are the 3D images that we showed. 200 patients fully sampled. We have the case space. But for the same images, we also have the segmentation masks for multiple different tissues. We have classification reports, and we have lesion bounding boxes too. So we're really trying to make that a resource for the community. We're trying to do some QC on it for now. But that's a really tricky problem. I don't have a good answer for you as to what is a good metric, but I can tell you that I really dislike PSNR as a metric. It just encourages very smooth images. So you can actually hack the PSNR metric pretty well, and you can show that you're seeing like a 1 or 2 dB improvement, but the underlying image manifold that you're learning is just very smooth. And it makes sense, right? Based on the formulation of PSNR, we're trying to minimize MSE loss. And if you have a little bit of a noisy image, the optimized MSE loss will just be like a smooth hyperplane that exists in your image. So we should not use PSNR, if you ask me, and maybe this is being recorded, so I shouldn't say things like this. Structural similarity is a little bit better, but I think that is probably.
I mean, apart from numerical metrics, is then the way to go show it to 10 radiologists and then ask them to say, which image is the best one to basically diagnose, regardless of whatever the RMSE or so. Yeah. What is? Yeah.
In an ideal world, absolutely, but I think that's very hard too, because even if you show it to a radiologist, all the example images that I showed here, they're knee MRI scans. If I show that to a neuroradiologist, they'll only be looking at overall image quality. They'll be looking at SNR, but they won't be conditioning their metrics based on the relevant pathology. If I show an MSK radiologist brain MR images, maybe they won't know what an MS lesion should look like. Is that a vessel? Is that a small enhancing structure? So it becomes very hard, I think, to come up with a fully data-driven model for that. And I think that's the biggest problem for the vision community broadly too. And I guess we can talk about the medical vision community too, is can we quantify image quality somehow? And can we supervise over that? And very hard problem.
But I guess it's a great effort from your side that you published this data set now with the bounding boxes and so on, which should open up
soon. Yeah.
Thank you very much.
Yeah, I think that the hardest thing over there is we want to share it. Our lawyers are less excited for us to share it. The method at Stanford is someone has to manually review everything. So every single image, someone has to manually look through K-space. It's just the rule. They have to manually look through all the bounding boxes too. So just a lot of hoops to jump through. That's why things go slower than normal, but that's the goal.
So I have another question. If you go back to the this upstream and downstream test instead of AI, I think it was one of your first slides.
Yeah.
What would be the how could you effectively combine these two? Actually, would that to be some test-driven reconstruction or something like that?
Yeah. So I mean, for example, with the data set that I mentioned, if we have the K-space and we have some bounding boxes that we care about, and these are pathologically useful. We have some segmentation masks for tissues we care about. I would argue that creating and reconstructing an image is useless. The image in and of itself has no value. What is valuable is what can you learn from the image? What sort of clinical insights can you draw into it? So if you can optimize for those insights and optimize in a supervised manner, then we're drawing value. So I think some sort of multitasking model, we're not just creating an image, but you're enforcing those pathological constraints simultaneously, will probably be the best way to go. We're trying, and the challenge there is to create the right data set too. So we're trying to help from that regard.
I see. Thanks.
Okay, if there are no more questions, I think we should thank Akshay for basically sharing this at a very inconvenient time for you. I think you had to wake up very early for this.
Now I have the full day in front of me, and I have 1.5 hours before any meeting starts. I'm actually excited to code a little bit.
Okay.
Awesome. Well, thank you for the questions. And please feel free to reach out, akshay@stanford.edu. Happy to chat more about this anytime.
Thank you very much.
Thank you very much. Bye bye.
Thank you. Bye-bye.
Yeah. Bye.
Thanks a lot.